Alright guys, so today we're going to be talking about higher order derivatives and concavity. So this starts off with the fact that we talked about the first derivative and we talked about the various applications of derivatives, such as optimization problems and related rates. Now we'll talk about higher order derivatives, like the second derivative or the third derivative. So we do know that as f double prime of x, because the first derivative was said to be f prime of x, so the second derivative would be f double prime of x. And, excuse me, or we can write it as f2 of x. That's not squared, it means the second derivative of x essentially. Now that being said, the third derivative then would just be f triple prime of x, and then so on and so forth. Nothing too crazy. And then, so if I have f of x, right, equal to 5x to the, that's the derivative, I'm just kind of getting ahead of myself, sorry. If f of x is equal to x to the 5 plus 4x to the 4 plus 2x cubed plus 5x plus 3, right? F prime of x is easy. We've done that before, just the basic power rule, right? And we get out of the way in about a couple seconds so you can take a look for yourself. But the power rule is basically what we call light work. It's pretty easy. You get that value right there. That's f prime of x. F double prime of x would just be the derivative after that. It'd be 20x to the 3 plus 48x squared plus 12x, right? That'd be f double prime of x, and triple prime would just keep going. This gets ugly when you have like the double prime for like a rational function, right? But for these power rules, we can do these all day. We just keep, taking it down. And that's what they do here. I don't care to keep going because we all know how to do the power rule. But let's take a look at maybe something a little bit uglier. Something like, pardon me, f of x equals cos x plus ln x, right? So what happens if I take the derivative, the first derivative, f prime of x equals negative sine x plus 1 over x, right? Let me get out of the way to make sure you can see that. F double prime of x would just be the derivative after that. Well, the derivative of sine is cosine x, and then this would be x to negative 1, so you drop the minus 1, and then get that, basically. You would basically factor out, well, not factor out, but kind of take out the constant negative 1. And then the derivative of sine is cosine. It's not negative cosine, it's cosine, but the negative just stays in front right there, right? And this would have been the same as x to negative 1. You drop it down and then take 1 away. X to the power negative 2 is 1 over x squared, right? And we can keep going with like third derivatives and all the other jazz. So we talk about, like, in physics and calculus kind of interconnect at some point when you take higher order, higher level physics, pardon me. So if you have the distance f of t equals t cubed plus 3t, right? These are t's, that's a plus sign. The first derivative would be what we call velocity. That'd be velocity. That'd be the change in position per unit of time. The change in velocity is the second derivative. That's also known as acceleration. So that's 6t plus 0, so that's really just 6t, pardon me, for the acceleration. And then note, we're asking for the acceleration at 2 seconds. So we sub 2n to f double prime. So 6 times 2, which is 12. Therefore, the acceleration is 12 meters per second squared. And there is a direction because acceleration indeed is a vector, so I should technically put that in. I think this is cutting in the way. Hopefully it doesn't get too distracting if I do this. There you go. So that covers most of the node. I mean, it's nothing too crazy. We've done derivatives. We're just taking second and third derivatives, right? So, concavity. That basically tells you if the graph is opening up or down. That's what concavity is. So f prime is the rate of change of f. F double prime so the second derivative is the rate of change of the first derivative. So if the first derivative is the slope, right? Just draw these like tangent lines. Then the second derivative tells what we call concavity. Okay? So if f prime of x is greater than 0, we're increasing. And if f prime of x is less than 0, we're decreasing. We got a way so you can copy that down your notes. And then if f double prime of x is greater than 0, that means f prime of x is increasing. If double prime of x is less than 0, it's a less than sign. F prime of x is decreasing. Okay. So that means the slope of the tangent line, if f prime of x is increasing, right? So if the second derivative is positive, that means it's what we call concave up. And then underneath here, this would be concave down. Okay. Excuse me. So if that's the case, and that's what it says in the note, that if f double prime of x is greater than 0, it's concave up. If f double prime of x is less than 0, it's concave down, basically. So, we talk about inflection points. Inflection, it's an F. So we talked about critical points. Critical points are when the first derivative is 0 or undefined. Inflection point is if concavity changes. Concavity changes at that point. So if it goes from concave up to concave down, we call it an inflection point. So if f double prime of c equals 0, or f double prime of c does not exist, that's a potential for an inflection point. Seems really similar, because for critical points, right, it's f prime of c equals 0 for the first derivative, and f prime of c does not exist. That would be critical points. Now we're talking about the second derivative. So if f double prime of c is 0, or f double prime of c does not exist, so we call it an inflection point. Okay? So to really like this, there's a space right here. If you go from here to here, right here roughly would be an inflection point. We go from concave up to concave down. Right here would be what we call an inflection point. Okay. So we call intervals of concavity. So intervals of concavity tells us when the function is concave up or concave down. So if f of x is equal to 3x to the 5 plus 5x to the 4 minus 20x cubed plus 4, then f prime of x, again, I'll get out of your way so you can get this down in your notes. F prime of x would be 15x to the 4 plus 20x to the 3 minus 60x squared plus 0, because the constant is a horizontal line, and the slope of the horizontal line is indeed 0. So that's the first derivative, but let's take the second derivative of the first derivative. Sorry, the second derivative of the function, or the derivative of the first derivative, to say that properly. So it's 60x to the 3 plus 60x squared minus 120x. The thing is, I can factor out a 60x out of all these terms. It's a common factor. Product of -2, sum of 1. I'm just going to cheat a bit and just look at my notes here. X plus 2, x minus 1. So what values make the second derivative 0, or does not exist? X equals 0, x equals -2, and x equals 1. Well, indeed, it's a polynomial, so there's no discontinuities. Polynomials are indeed continuous. So there's nothing that makes the second derivative not exist. Usually, we make it with a line, but it seems like based on the notes, they said x is the element of -infinity to -2 is concave down. -2 to 0 is concave up. But really, I guess what we can do is just plot these on a number line. Right? So I put something less than -2 in here, like -3. We got a negative and a negative with a positive and a negative, so it would be negative if I put a value less than -2 into my second derivative. So it'd be concave down, CB. Between 2 and 0, the value could be -1. So put -1 in here. I get a positive here, a negative here, but a negative there. So it'd be actually positive, so it's concave up. And then between 0 and 1, put a half in here. I get a negative right here, a positive here, and a positive here. So I'm negative again, so I'm concave down. And then if I put something big, like 100 in here, I get a positive, positive, positive. So I go concave up. So indeed, I'm concave up. X is the element of -infinity and -2. And no, that's concave down. Concave down, pardon me. Concave down from x is the -infinity to -2. I'm also concave down, and x is the element of 0 and 1. And I'm concave up, let's go right down here, from -2 and 1. 0, sorry. 0. And also 1 and infinity. We don't include infinity again. We never put square brackets. We put round brackets for infinity. So that's fine and dandy. You can just keep going with like different types of functions. What I want to cover though is what we call the second derivative test. What is the second derivative test? We learned about the first derivative test. Okay? a second derivative test, SDT. What that is that if f prime of c equals 0, or f prime of c does not exist, then notice that these are critical points because they have to do when the first derivative is equal to 0 or the first derivative does not exist, right? So we call critical points. So if f double prime of c, what's c? C is not an inflection point. It's a critical point. That we're denoting c as a critical point. If that's greater than 0, then you have a local min. The reason for that is because it'd be concave up, and you'd have a local minimum. If f double prime of c is less than 0, c is a local max. It's concave down. So if I have this, if I do f prime of c, I common factor that. Product of minus 3 sum minus 2. 3 and minus 1. I mean minus 3 and 1. So if I were to actually solve this, set f prime of x equals 0, my values would just be x equals 3 and x equals minus 1. So f double prime of x is just going to be 6x minus 6. Okay? So I sub in these critical points, which made the first derivative 0 does not exist, into the second derivative. So what happens is we go f double prime of 3. That's like putting 6 times 3 is 18. It's positive, right? And f double prime negative 1 is negative, right? If it's negative, that means that negative 1 is a local max, okay? And this would be a local min, just because it's concave up when it's positive and it's concave down when it's negative. So that's a quick way to tell what's happening at those points, okay? That's the second derivative test.